Okay, so welcome back again. We're up to part 2, and what we're going to be looking at next is the phase 1 problem for linear programs. So what we've talked about so far is the simplex method, and the starting assumption for the simplex method is that we have an initial basic feasible solution to start with. Okay, now for a big problem, finding a point that is actually feasible is quite a big problem in itself, and it actually turns out that it's almost as much work as solving the linear program. Okay, so we call this problem the phase 1 problem. Okay, and basically the problem is find an x satisfying all constraints. Okay, and so for, e.g. for standard form LP, it is find x such that ax equals b and x is component-wise greater than or equal to 0. Okay, so that is called the phase 1 problem. Notice it's only a problem on the constraints. It doesn't involve the cost C transpose x anywhere. Okay, so this is a more general problem than the linear program. At any time you need to find an x satisfying a set of constraints, then you're solving what we call a phase 1 problem. So what we're going to do in this part of the lecture is we're going to go through 3 different cases, 3 different ways of doing that. Two of which are general, or at least they work for standard form LPs, and one of which sometimes works if you've got your LP in a particular convenient form. So case 1 is what we call the all slacks basic case. Okay, and this works if your LP can be written in a particular way. So if the LP is of the form minimize C transpose X subject, I suppose that the cost is actually irrelevant, subject to some inequality constraints, and we're going to add the extra restriction that the right hand sides are greater than or equal to 0, and non-negativity constraints on our x variables. Then adding slack variables for each of the ax is less than or equal to b inequalities, so S in Rm gives, so I'm just doing this in the same way we normally do for standard form, constraints A Im x s equals b. Okay, so I'm just adding in one s for each inequality to make it an equality like we've been doing previously. Okay, and x and s are greater than or equal to 0. And if we just use the last m variables, i.e. the slack variables, okay, that's just the last m variables as the initial solution, so our initial basis, gives an initial basic feasible solution of x s equals 0 b, which is greater than or equal to 0. Okay, so if we have a nice inequality form LP with additional non-negativity constraints and non-zero right-hand sides, then we can just set the slack variables to be our initial basis and we're done with it. Okay, and that's why the example that I did previously worked straight off, is because I had it in that form to start with. Okay, so that one, usually you can't do that though, because usually your linear program will be like in standard form or something like that. Okay, so that takes us to our next case. The standard form the method by which we call artificial variables. Okay, so we've got an LP, we've got standard forms, so constraints ax equals b and x greater than or equal to 0. Okay, we're going to also have b greater than or equal to 0. We can do this by multiplying any constraint with b less than 0 by negative 1. Okay, that's not going to change an equality constraint, but if we multiply by negative 1, we can force the right hand side to be greater than or equal to 0. So now we introduce what we call artificial variables, and they'll be xn plus 1 through to xn plus m. Okay, and what are we going to do? Well, basically we're going to add on one extra variable to each of the constraints. Okay, so and add 1 to the left hand side, sorry. Of each constraint. So we're going to get e.g. the ith one, ai transpose x equals b, goes to ai transpose x plus xn plus I equals b. Okay, so we're adding in these extra variables. So basically the problem we're doing now is actually changed. We're adding in an extra variable to each of the constraints, and now our set of constraints sorry, let's not get rid of all that. Now is a im times x1 through to xn plus m equals b. Okay, and if we make this into a problem by minimizing xn plus 1, the sum of xn plus 1 through to xn plus m, subject to these constraints, then what we have is a linear program. Whoops, let's not do that. Okay, let's have a think about that for a second. What does this linear program here mean? Well, if we want a vector of x's that satisfy our original constraints, these ones here, then the only way that works is if each of these artificial variables are equal to 0. Okay, if each of these artificial variables that we've added on are equal to 0, then the x that we have left is going to satisfy all of the original constraints. So the way we can ensure that is by minimizing the sum of those extra variables. They're constrained to be non-negative, and if we can find a basic feasible solution to the original problem, or sorry, an x that satisfies the constraints to the original problem, then we'll be able to do that with this sum being equal to 0. So solving, this is called the phase 1 problem. Okay, it's a linear program. It's got constraints related to your original ones, and solving it yields an initial basic feasible solution if one exists. Okay, because if one exists, if we can find an x that satisfies the original constraints, that means we must be able to get all of these x's, these extra artificial variables, to 0. If we can't do that, then there is no basic feasible solution to your original problem, or is no feasible point. Okay? So if the phase 1 solution does not have xn plus 1 equals xn plus 2 equals xn plus m equals 0, the original LP constraints, are infeasible. Okay. So we have an LP to solve. To solve that, we're sort of going around in circles here, because we've still got an LP to solve, and we still need an initial basis to solve that one. Okay, because we're going to use the simplex method to solve that linear program too. But the good news is, this problem has an obvious-ish initial basis, and it's those artificial variables. Okay, so if we choose that basis, then xb is equal to im times inverse b equals b. Okay, and which is greater than or equal to 0. So it's easy to come up with an initial basis for this linear program. Solving this linear program, if it gives us, if we can get it down to 0, it gives us a basis that we can use to solve our original linear program, subject to these constraints here, and that's called the phase 2 problem. So the basis B that optimizes the phase 1 problem can then be used as the initial basis for the phase 2 problem. Which, as we know, is the original LP. Okay, so this method basically involves introducing m new variables, and it always works for these set of basis vectors, so long as some conditions that we'll talk about a bit later hold. Okay, so this is kind of an approach that always works. The only slightly irritating thing about it is that you have to introduce a reasonably large number of extra variables. As you can imagine, solving this linear program here, the phase 1 problem by the simplex method, is quite computationally expensive in itself. It's often as much work as solving the actual linear program you're interested in. Okay, so that's one method. There is one more that we'll look at. Once again, we'll look at this method. Just uses one artificial variable. Okay, so again, we have constraints ax equals b and x greater than or equal to 0. So what we do this time is we choose an initial basis b for which AB inverse exists. Okay, so we're just trying to choose basically m independent columns of our matrix A. That's not too hard. You can do it by Gaussian elimination and choosing some pivots. Okay, that's pretty straightforward. if xb is greater than 0, greater than or equal to 0, sorry, we have an initial basic feasible solution, and we're done. Otherwise, let xj be the most negative element of xb. Okay, and we'll have, obviously j is an element of our basis. Okay, so we're going to compute xb. Okay, and compute xb equals ab inverse b. Okay, so we're going to, if we don't have an initial, if it's not feasible, our xb, we look at the most negative element and we introduce an artificial variable xn plus 1 and when we introduce a new variable, we've got to introduce a new column in our matrix. So with the corresponding column of A given by A n plus 1 equals B minus the sum of the columns from the basis vectors plus one copy of AJ. Now this all seems kind of strange at the moment, but we'll see why we're doing this in a second. So we'll define a new basis and I'll call it B sharp. And that's going to be our original basis minus j, because the xj is the most negative element, plus our new artificial variable. So we're going to swap out that xj for the artificial variable. Then the sum over the new basis vectors of the columns of A equals B. Okay, you can see that by just plugging it in, by plugging in by star. Okay, so if you don't believe me, just plug it in and you'll see it comes out straight away. Okay, therefore, A B sharp, another way of writing that is just A B sharp times 1 equals B, which means that 1 equals our initial xb, which is A B sharp inverse B, where, as I've said before, 1 is the vector of all 1s. So, B sharp is an initial basis, so it's feasible for something. For the phase 1 problem, minimize xn plus 1. Okay, so we're just minimizing that artificial variable. Subject to these constraints here: an plus 1, x1 through to xn plus 1 equals b, and x is greater than or equal to 0. Okay, so once again, we've got a phase 1 problem that if we solve it, it'll give us an x that satisfies our initial constraints. Okay, so if xn plus, so if we can so we're minimizing xn plus 1, x is constrained to being non-negative, so the lowest it can go is 0. If we can get to 0, if we can get it down to 0, then we're going to, this new set of equality constraints is going to reduce itself to our original ax equals b. Okay, if xn plus 1 is 0, then we don't need to worry about an plus 1, and we'll just have ax equals b. So if we can get this 0, if we can minimize this, and the answer is 0, xn plus 1 will be non-basic. We'll have a new basis, a new basic feasible solution that satisfies ax equals b, and x is greater than or equal to 0. Okay, so if xn plus 1 is non-basic in the solution to the phase 1 problem. Okay, so if it's non-basic, it'll be 0, and the cost will be 0. Then the optimal basis B can be used as an initial basis for the phase 2 problem. And that will be our original linear program. So this way has some advantages over the previous one. The best thing about this method is that it only involves introducing one extra artificial variable. Okay, the method we did previously, which was this one here, was a wee bit harder than that because, well, a wee bit more clumsy because we had to introduce m new variables to solve this problem. That's going to equate to a bit more computation. The one we've just done now is a bit neater, but a bit more complicated to think about. But the nice thing about it is it only introduces one extra variable, so it's better computationally than the previous one. Okay, so why don't we just do a quick example, and then we'll call it a day. So, quick example, he says. So, consider the LP minimize some cost. Don't forget, I don't really need to even be worrying about the cost at the moment because they're not relevant to the phase 1 problem. The phase 1 problem is just worried about finding an x that satisfies all the constraints. So let's just jot this one down. Less than or equal to -4. 6x1 minus 5x2 plus 2x3 is greater than or equal to 15, and 3x1 plus 2x2 plus x3 is less than or equal to 15, and the x's are greater than or equal to 0. If we convert this to standard form, which I'll let you guys do, okay, so you can either pause now and do it as an exercise, or you can just trust me. The constraints ax equals b, x greater than or equal to 0, where x is now in R6. We're going to add in 3 slack variables. So the matrix A in our standard form looks like this: 4, 2, -1, 1, 0, 0, -6, 5, -2, 0, 1, 0, 3, 2, 1, 0, 0, 1, and our right hand side is -4, -15, and 15. Okay, so we've added in 3 slack variables. These are the constraint matrices for our standard form. So, first thing you might try, the kind of naive approach, is to try the last 3 variables being our basis. So if we tried all slack basis, which is 4, 5, and 6, then our xb is just going to be b, and it's got some negative numbers in it, so it's not going to work. So we can't do that. All-Slack's, we'll start with that anyway though, the All-Slack's choice of basis is okay, because they will give us an AB that exists, AB that is invertible, sorry, giving XB equals -4, -15, 15. Okay, which is not feasible. So we're into our otherwise case. So when we look at the element of XB that is most negative, which corresponds to is most negative, so we introduce artificial X7 and look at the new basis B sharp equals 4, 7, and 6. Okay, the new column of A is A7, just applying the formula from before, B minus the sum. Okay, let's have a look at the formula. B minus the sum of the basis of the try that again. B minus A4 minus A5 minus A6. B minus the sum of the basis columns originally plus A5, which equals B minus A4 minus A6, which if you check for yourself is equal to -5, -15, and 14. Okay, so the phase 1 linear program is minimize over x, x7, subject to A, A7, x, x7 equals B, and our x's are greater than or equal to 0. And if we solve this LP and our answer and our optimum is 0, so x7 is not in the basis and it's equal to 0, then we'll have ourselves an initial basis that we can use to solve our original linear program in standard form. Okay, so let's just verify that this does actually give us a basic feasible solution. So initial basis for the phase 1 problem, we have A B sharp equals A4, A6, A7, A6. Just fix that. Equals this matrix here, 1, 0, 0, -5, -15, 14, 0, 0, 1. And XB sharp equals x4, x7, x6 equals A, B sharp, inverse B. Check for yourself in MATLAB by doing this matrix \B, and that should give us 1, 1, 1. Okay, which is greater than or equal to 0. feasible for the phase 1 problem as desired. Okay, so that's what I'm going to do. That's all I'm going to do today. So what we've learnt about is we did an example of the simplex method on an actual problem, but we realised that it's no good knowing how to do the simplex method if we can't figure out a way to get ourselves an initial basis. So what we've looked at is 3 different ways, one of them is not usually practical, of finding an initial basic feasible solution with which to start the simplex method off. Okay, and they both involve creating a different linear program to solve, which actually turns out to be approximately as much work as solving the original linear program itself. So, but we find an initial basis by solving a linear program, and then we can use that initial basis to solve our original LP. Okay, so this is why we talk about phase 1 and phase 2 problems, because we have 2 linear programs to solve, and the first one, finding the basis, is phase 1, the second one, solving the original LP, is phase 2. Okay, so that's all from me for today. I'll catch up with you back in class next week. So we're still in Kotuku 101 as far as I'm aware. Okay, so on the timetable. See you later.